This design is called the fully crossed design. And I was saying a little moment ago, it has the most statistical power for a given number of readers and a given number of cases with verified truth. So we need this condition, otherwise Marina and I will disagree. And she has a great point, by the way, and we intend to study that paper by Nancy and go through that in detail. Frank Samuelson is actually working on this problem. Frank is in the back there. Looks like a Dutch artist, actually. That's the fellow. That's Frank. Okay, so this is the most statistical power for a given number of truth-verified cases, and so it's the least demanding on resources, and we have the commission from Congress to assist sponsors to find the least burdensome path. And so we have to keep this in front of our eyes when possible. Now, a few anecdotes. Bill Sachs and I always talk, he'd always say, well, here's the performance, Bob. I'd say, Bill, that's the mean. That's the average. That's the point estimate. What does that mean? That's easy. For statistical inference, you're interested in the uncertainties. You want to get error bars. This reminds us, some of you have been exposed to my shtick for a long time, we have the allegory of the 6-foot statistician. And I think this really was told about John Kenneth Galbraith, the 6'6" economist. What happened to this person? He drowned. He was wading in a stream that had an average depth of 5 feet. My delivery is off. It's the fluctuations. It's not the mean. It's the fluctuations that are important. There's a very famous quote from Jim Hanley, who was a statistician at McGill in Montreal. He said, look, you're all looking at the results of this study. This study happened once. It's never going to happen again. That's why you get error bars. People who are not statisticians, they think, well, you know, confidence intervals, error bars, that's some little field that the statisticians will generate these, and they'll give them to us and say, well, it's statistically significant or not. That may be true, but you've got to get into the error bars yourself, because from the point of view of classical statistics, what the error bars mean is you are trying to estimate the range of performance you would see if you redo that experiment many, many times, each time drawing a new fresh sample from readers and cases. And so when you show the error bars, you're saying, I don't necessarily expect to see the result I just got tomorrow. I'm going to get a spread like this. That's the classical frequentist interpretation of that. It's your best estimate with your given data of the spread that you expect to see. So just don't relegate this to the statisticians. The real world is actually messy because of finite samples, and you get that spread. So you actually have to talk about replications of experiments and report to your readership, report to the center, what spread do you expect to see.